And we basically said that temporal summation is if you have the same stimulus in terms of the location, but it's back to back. It's close enough together in time, and you can add those two graded potentials. And I just wanted to specify that it doesn't always have to be two positive or two depolarizing changes to the membrane potential. It can be positive, negative, it can be two negative, it can be two hyperpolarization, two depolarization, and it can be more than two. This is another thing I wanted to just really clarify. It can be several. We looked at the axon last time, and we talked about the soma, and there were several synapses happening on the soma of that neuron. So again, it can be multiple synapses. As long as they are close enough in time, they can be summed and potentially get us closer to the threshold. Or it can be spatial summation, where it's different locations on the soma, right? And then if they are overlapping in time, then it can be spatial summation, right? But again, it can be multiple different stimuli, or it can be multiple stimuli at the same exact spot, which is temporal. Okay, having said that, let's go on to our checkpoint question here, which is why are graded potentials unable to communicate over long distances in time? And just to kind of go back and explain this one, we mentioned that graded potentials dissipate. They're not strong enough membrane potential changes. Even if it's a depolarization event, if it doesn't get to threshold, it's going to dissipate. It's not going to be able to travel beyond the axon hillock. So the strength of the signal must be greater than 55. So when we add all of the various graded potentials that are being received on different spots or the same spot, close enough in time on the soma of our neuron, if it's not a strong enough combined signal, by the time it gets to the axon hillock, then it simply diffuses or dissipates, right? So that is why graded potentials cannot move down the axon hillock. Okay, and that basically means that they're decremental. Okay. So let's move on to our second learning objective here, which is to explain the ionic basis of the action potential and describe the gating mechanisms for voltage-gated sodium and then potassium channels. And when we say gating mechanisms here, we're looking at the state of our sodium and potassium channels. So we really want to recall what we said last time about the location of these different channels on various parts of the neuron. So just to recap what we mentioned earlier here, here's our membrane potential versus our resting potential at -70. Here is our depolarization. Remember, we said that a depolarization is a positive membrane potential change from -70, which is the resting membrane potential value. And then we can also have a repolarization, which is the second phase of the action potential. And that is where we go from a positive membrane potential to returning back to rest at -70. So repolarization is one type of negative membrane potential change. And then the other type of negative membrane potential change is the hyperpolarization. So this is where we go below resting, which is the -70. And this is typically when we engage potassium's movement. And we want to remember here that sodium is comfortable way up here. Remember, sodium has a equilibrium potential at +60. So all the way up here is +60. Potassium is at home way down here. So potassium's equilibrium potential, -94. So when we look at the movement of these two ions, remember, they're going to be moving in order to achieve their equilibrium. So if I open up more sodium channels, sodium is going to rush into the cell. Remember, it has a really strong current, a really strong ECDF. And so that's what's responsible for this initial upstroke in the action potential. This is sodium's movement as a result of opening up sodium channels. For potassium, it's the opposite. So potassium is going to be comfortable when the membrane potential is negative or below rest. And so when we open up potassium channels, potassium will move out of the cell. Again, it's positive. So when it leaves the cell, it's going to help return that membrane potential closer to rest. And in some cases, it's going to go below rest, right? So this is also going to be potassium's movement. Okay, so whenever we have a depolarization, sodium is responsible for that. Sodium's movement into the cell is what results in that positive membrane potential change. And then whenever we have a hyperpolarization or a repolarization, potassium's movement out of the cell is responsible for that membrane potential change. Let's also recall what we described about the location of various channels along the membrane. So as we're looking at the movement of ions, we want to remember what are the transport or channels that these ions are using to move through the neuron. So first we have leak channels. And these are throughout the neuron, right, all over throughout the axon, soma, axon terminal, etc. And they're responsible for the resting membrane potential, right? We discussed that quite a bit last week. Then we have the ligand-gated channels. And ligand here means that something has to bind to this channel. So this is going to be found on the dendrites and the soma, or the cell body. So again, this is going to be responsible for the signal transmission from a presynaptic neuron onto the cell body of a postsynaptic neuron. So when a chemical is released from that presynaptic neuron, it's going to have to bind to this ligand-gated channel in order for that channel to open up. Then we have voltage-gated channels. These are the most important with respect to the action potential. The voltage-gated channels are going to pick up the signal if we do get to threshold. So if the membrane potential gets to -55, then the voltage-gated channels are opened up. And so that's what we mean by voltage-gated here. When we get to a specific threshold or a specific membrane potential, then this channel will open up. So it's really important to think about the mechanism of these channels, which we're going to spend some time describing later on. These are also found throughout the neuron, but really concentrated along the axon, especially at the axon hillock. Then there are the calcium channels, and these are at the axon terminal. So these are going to be responsible for releasing the neurotransmitter or the chemical compounds that are going to come back up here and bind to these ligand-gated channels. So we can begin to see how one axon terminal releases the neurotransmitter. The neurotransmitter crosses the synapse, and then it's going to bind to this ligand-gated channel, and then that's going to result in the signal transmission from the terminal of one neuron to the cell body of the adjacent neuron. Looking more specifically at the way that the channels open up, so basically changes in the membrane potential, which are controlled by the flux of ions. This is what was responsible for opening up, or in some instances, closing the gated channels for potassium and sodium. So for potassium, we have some leak channels. So remember, potassium has a much higher permeability when the neuron is at rest. So there's significantly more leak channels for potassium. But then there are also voltage-gated channels that are going to open up when the membrane potential gets to a certain value. And we'll talk about what that is. These specific voltage-gated channels will be closed when the neuron is at rest. So they're not necessarily contributing to the resting membrane potential. And then for sodium, similar situation. So sodium has many voltage-gated channels, again, more concentrated along the axon and more so at the axon hillock, and then very few leak channels. So just to recall that sodium has a very or a lower permeability with respect to potassium. So there are much fewer leak channels for sodium, especially when the neuron is at rest. And then I just want to bring back this drawing from last time, just to recap some of this. So here's our presynaptic neuron. Here's the axon terminal. We're going to release neurotransmitter here. It's going to bind to ligand-gated channels that are located on the soma. And then when those ligand-gated channels open up, ions are going to begin to flow. And this is where we have several graded potentials arriving on the cell body. From there, at the axon hillock, we determine if those graded potentials are sufficient to achieve the -55 millivolt change. And if they are, then voltage-gated channels along the axon hillock and axon will open up. Sodium or potassium, right, both of those ions will move respectively. That's responsible for the action potential, which then moves down the axon. And then when the action potential gets to the axon terminal, it's going to result in the release of opening up calcium channels here, which further releases more neurotransmitter, and we keep the signal moving from one neuron to the other to the other. And this is how neurons communicate. Okay, so this is the purpose of the action potential. It's a way to turn chemical energy into electrical energy and then back into chemical energy and help to pass that signal from one neuron to the other. Okay, let's see, quick question here. So is the resting membrane potential more due to leak channels or the sodium-potassium pump? Excellent question. So it's really a combination of both, right? The leak channels are going to be resulting in passive movement of the ions, and the sodium-potassium pump is just actively moving those ions in the opposite direction. This is how we end up striking that balance, that steady state, where there's no flux, there's no net accumulation of the ions on either side. So there's always going to be more sodium outside the neuron and more potassium inside because of the balancing act that the sodium-potassium pump helps to achieve, right? If we didn't have the sodium-potassium pump, we would just have ions leaking, sodium leaking in and potassium leaking out. And so those ions would begin to accumulate if we didn't have a way to bring them back actively in the opposite direction. So both of those structures are essential to the resting membrane potential. Okay. All right. Okay, what we're going to move on to look at here is the gating mechanisms on both sodium and potassium channels. Now, sodium's gating mechanism is slightly more complex, so we're going to start with that one first. Potassium is somewhat easier, and so we'll look at that afterward. So when we think about a sodium voltage-gated channel, it's going to have two gates and it's going to have two states. So these channels are going to open up when the membrane potential is depolarized to -55 or beyond, right? We can have a stronger graded potential that takes us beyond -55, but this is the threshold value that must be met. Sodium is going to rush into the cell according to its electrochemical gradient. In other words, it's ECDF. Remember, it has a strong current into the cell. And this is going to help the membrane potential to start climbing in an attempt to move towards sodium's equilibrium potential, which is really positive, at +60. Now, these channels are going to be deactivated at +30. So the membrane potential will never actually arrive at +60 because the deactivation mechanism on these channels closes them at +30. All right. So if we look at the states and the gates of these channels, here's the activation gate, and then here is the inactivation gate. So when the neuron is at rest, this is the state of the channel. The activation gate is closed and the inactivation gate is open. So essentially, the channel is prepared to be depolarized, but it's not depolarized yet because the activation gate is what will open as soon as we get to -55. But because the inactivation gate is open, it's ready if a positive membrane potential change does come along to -55. So let's say that happens. Now we have depolarization, and now both gates are open. So the activation gate is open, the inactivation gate is still open, and now sodium can move freely from the extracellular space into the cell. So this is what is responsible for that further membrane potential change. In other words, the depolarization or the upstroke of the action potential. Now, the other component here is that the activation gate is going to open, but there is a timed component here. So the inactivation gate specifically is going to close after 1 millisecond of sodium moving through the channel. So when we get to -55, a timer goes off, and after 1 millisecond, the inactivation gate is going to close. So in this state, this is the third state of the channel. The activation gate is still open, but the inactivation gate is closed. So the channel is closed and it is incapable of allowing sodium movement because we need to get the membrane potential back down to rest. And then we're going to return the channel into this initial state where it is ready for depolarization because the inactivation gate is now open. Okay, so these are the three states of our sodium, our voltage-gated sodium channel, especially thinking about the voltage condition, so that -55 must be met to trigger depolarization, and then the time condition for the inactivation gate, which says that after 1 millisecond of depolarization, the inactivation gate closes, and now we can no longer have movement of sodium until we return the membrane potential back to -70, and then we return the channel to its initial resting state. Okay. So just to kind of reiterate the activation gate conditions. So it is voltage dependent, right? It needs to get to -55 in order to open. It is going to result in depolarization as soon as it is open. And this is an example of a positive feedback change. Why positive feedback? Because we're moving away from our set point. Our set point here is -70. And if we move away from that by making the membrane potential more positive, then for a short period of time, but for a desired outcome, we are actually enacting a positive feedback change. However, this is going to feed into a larger negative feedback when we look at potassium's movement. So this is a desired outcome for a short duration of time where we move away from the set point condition. The inactivation gate mechanism is that it is voltage and time. So the activation gate is only voltage dependent. The inactivation gate is both voltage and time dependent. So this is that time condition where it will close after 1 millisecond of depolarization. So yeah, it's going to open for depolarization, and then that 1 millisecond timer goes off, and then it will close after that 1 millisecond.